Welcome to the Health Headliner podcast by Tudu Digital. Our content is informational only and not medical advice. Please consult your provider. Now, let's dive into today's headlines.
Okay, imagine this. You're finally drifting into that perfect, deep, restorative sleep, the kind where the world just melts away and you're completely out, perhaps dreaming of, I don't know, a calm, peaceful escape.
Yeah, we all want that.
Right.
Yeah.
Now, here's the thought. What sound, no matter how quiet, could possibly cut through that profound slumber and grab your attention instantly, even before you're fully awake?
It's not just any noise, is it?
No. It has to be something truly jarring, something that signals a primal, immediate urgency.
That's the perfect scene setter, because today we're taking a deep dive into precisely that fascinating phenomenon.
How our sleeping brain does it.
Exactly. How your sleeping brain manages the incredibly delicate balance of disconnecting from the world for essential rest, yet remaining acutely alert to very specific sounds that signal danger.
And here's where it gets really interesting for us. We're unpacking the groundbreaking findings from a study by scientists at the University of Geneva and the Institut Pasteur published in Scientific Reports.
A really solid piece of work.
Definitely. Our mission today is to explore their research on what they call rough sounds.
Rough sounds, yeah.
What exactly are these sounds? Why do they uniquely penetrate our sleep when others don't? And, well, what does this all mean? For everything from understanding certain auditory disorders to designing genuinely healthier sleep environments in our increasingly noisy world.
Well, what's truly fascinating here is that this isn't simply about how loud a sound is.
Right, not just volume.
No. It's about a specific inherent acoustic property. When we talk about roughness in sound, we're referring to rapid fluctuations of sound intensity.
Fluctuations. Like how fast?
Think of it as how quickly a sound gets louder and softer, happening incredibly fast, specifically between 40 and 100 times per second.
Whoa, 40 to 100 times a second. That's just mind-bogglingly fast.
Yeah, it really is.
I mean, to put that in perspective, our everyday speech, you and I talking right now, forming syllables and words modulates at a much, much slower rate, somewhere between 4 and 8 hertz.
That's right, much slower.
So these rough sounds are hitting our auditory system at profoundly higher frequencies, creating what most people describe as a truly shrill, almost gut-wrenching sensation, like a smoke detector or that piercing cry of a baby. It just immediately grabs you, doesn't it?
Absolutely. And this isn't an accident of acoustics. It's a design feature, if you will. This unique quality is precisely what makes these sounds so effective at their primary job. Automatically capturing our attention to signal imminent danger.
Right.
When you consider the classic examples, the blaring of an audible alarm, a human scream, or the piercing cry of an infant, these are all sounds inherently designed to break through everything else, including your deepest sleep.
So it's not just a subjective feeling of alarm. There's a direct neurological pathway involved here.
Yes, exactly.
These sounds seem to activate the amygdala, that small almond-shaped region in our brain that's essentially our ancient alarm bell. Is that the key reason they break through so powerfully?
You're right on target. That amygdala activation is absolutely key.
Okay.
And what's particularly significant here is that while we've long understood how the amygdala responds to threats when we're awake, well, its impact during sleep was largely ignored until this research.
Really? That seems like a huge gap.
It was a critical gap because naturally, recognizing threatening signals during sleep is crucial for survival.
This research really makes you wonder, how do you even begin to study something so subtle and unconscious? What was their ingenious approach to unlocking these secrets within sleeping participants?
Well, the researchers meticulously designed their study. They recruited 17 healthy volunteers and had them sleep in specially equipped rooms.
Okay.
Crucially, their brain activity was precisely monitored using an electroencephalogram, or EEG.
The EEG.
Yes. This allowed the scientists to track exactly what was happening in the brain without disturbing the participants' sleep.
So they had them hooked up to electroencephalograms. But then came the crucial part, the sounds themselves. I imagine they couldn't just play anything.
Yeah.
How did they design the auditory stimuli to really isolate what they were looking for?
That's an excellent question. The researchers played various types of human cries and what they called false cries.
False cries.
Basically manipulated sounds, all at a very low volume. The clever part was that they carefully manipulated both the pitch of these sounds and, critically, their roughness.
So they could separate pitch from roughness.
Precisely. The goal was to observe very specific brain responses without actually waking the participants, which, as you pointed out, is a key distinction from simply seeing if a sound causes someone to fully wake up.
Okay, so they're playing these sounds while people are asleep, meticulously watching their brain activity. What was the big, perhaps surprising discovery about how our sleeping brains truly react to these sounds? What's the core insight here?
The monumental discovery was this. It wasn't the pitch of a sound that mattered, but its roughness.
Wow, really?
Really, think about it. Your brain doesn't care if a scream is high-pitched or low-pitched. If it has that rapid, jarring quality, your ancient alarm system kicks in, even in deep sleep.
That completely redefines what we thought penetrates our slumber.
It does.
That's truly counterintuitive. So a low-pitched scream could be just as alarming as a high-pitched one, as long as it possessed that unique, rough quality.
Exactly.
It's the texture of the sound, not its tone, that's key then.
You've got it. It completely shifts our understanding of what constitutes an alarming sound, stripping it back to a fundamental acoustic property.
Okay.
And they observed two key phenomena that really shed light on this. First, rough sounds consistently triggered a brain response, unlike any other type of sound they tested.
Consistently.
It wasn't random. It was a reliable response every single time.
That's a powerful finding, that consistent brain response. So they saw the brain reacting. What else did they observe that was particularly telling about how our brains handle these rough sounds?
And another truly remarkable insight. These rough sounds significantly increased sleep spindles.
Sleep spindles.
Yeah.
Remind me what those are again.
Okay, so sleep spindles. These are short bursts of brain activity that are typically elicited in response to a sensory and potentially disturbing stimulus during sleep.
Bursts of activity.
Think of them as tiny, rapid electrical oscillations in the brain.
So it's almost like the brain saying, hey, I heard that, but I'm going to try and process it without fully waking up. That's a fascinating intermediate response, as you called it.
It really is.
But why is it so clever? Why not just wake us up completely every time there's a potential threat?
That's a brilliant question, and it points to a remarkably sophisticated filtering mechanism. While these rough sounds clearly signal danger, sleep spindles are actually also strongly linked to sleep maintenance.
Oh, interesting. So they help keep us asleep too.
Exactly. They're more abundant when our sleep is resistant to disturbances. So the brain might be using these spindles as a way to acknowledge a potential threat and check it out, essentially, running a quick internal security scan without deploying the full wake-up protocol.
Like a quick assessment.
Precisely. It's an incredibly efficient survival strategy, allowing us to stay rested while still being subtly vigilant.
And diving a little deeper into the neurological markers, the study found that screams evoked cortical responses with higher theta phase consistency during both wakefulness and non-rapid eye movement sleep. What does that tell us about the brain's reaction?
What theta phase consistency tells us, in simple terms, is that the brain's response was incredibly precise and uniform.
Okay, consistent.
It wasn't a fuzzy signal. It was a crystal clear, reliable alert every single time, across different sleep stages. This indicates just how hardwired this specific response is.
Wow.
And there's more. Screams also boosted sleep spindle power, which is a fancy way of saying the brain was really registering these rough sounds as highly important, giving them elevated salience.
So paying extra attention to them.
Exactly. Additionally, roughness increased early delta power, which is a marker of very deep, slow-wave sleep.
Even in deep sleep.
Yes. This further confirms that these sounds aren't just tickling the surface of our awareness, they're actively being processed even in our deepest, most restorative sleep stages. It's truly fascinating how deep this goes.
It's incredible to think that our brains are doing all this while we're completely unaware. This consistent, deep-seated response to roughness. It just feels so primal.
It absolutely is.
Is there an evolutionary reason why this specific acoustic property holds such a privileged status for our brains even in sleep?
You're hitting on a crucial point. Sound roughness is not commonly encountered in everyday environments.
Right, you don't hear it much.
No. In both humans and animals, it's typically reserved for urgent, high-stakes communication.
Like warnings?
Exactly. This suggests an adaptive communication channel that has evolved over millennia. Even at a very low sound level, roughness remains an efficient attribute to mobilize our attention systems during sleep.
So it cuts through the noise, literally.
It ensures that critical warning signals, like screams, can be optimally processed from a distance by sleeping individuals. Imagine our ancestors hearing the faint, distant scream of a tribal member.
Yeah.
Their brains were already processing it for danger, even in their sleep, enabling them to react quickly.
This research obviously has implications beyond just understanding how our brains work, extending to our health. How does this research impact our understanding of health and disorders?
Well, this research is vital for understanding disorders such as hyperacusis.
Hyperacusis, that's the extreme sound sensitivity, right?
That's right, a hypersensitivity and viral-day intolerance to certain sounds. For someone with hyperacusis, these rough sounds, which everyone's brain is wired to respond to, could become overwhelmingly distressing, even painful.
I can only imagine. And it goes beyond hyperacusis, doesn't it?
Absolutely. It's also incredibly relevant to other neurological and psychiatric conditions where auditory processing can be disrupted.
Like what?
Such as tinnitus, which is the perception of ringing or buzzing in the ears, epilepsy, and even Alzheimer's disease.
Really? How so?
Well, understanding how these fundamental acoustic properties affect the brain could very well lead to new insights and even new therapeutic approaches for these conditions. It helps us understand the basic processing.
And for all of us, living in increasingly noisy environments, especially in cities. I mean, this deep dive shows us why understanding how sounds affect our brain during sleep is vital for our physical and mental health.
Indeed. Think about it. Common human activities and even rough snoring sounds.
Rough snoring.
Yes, some types of snoring can actually generate these frequencies. This research suggests they could potentially disturb sleep by enhancing the recruitment of arousal-related brain circuits, even if they don't fully wake us up.
So even if you don't wake up, your sleep quality is being chipped away at.
Exactly. It's potentially a constant, subtle assault on our restorative sleep, which impacts everything from our mood and focus to our long-term health.
So while the study is groundbreaking and reveals so much, no research is without its boundaries or, questions for the future. What were some of the limitations or areas for future exploration here?
Well, one key limitation is that the study primarily focused on non-rapid eye movement sleep.
And REM sleep.
Right, which includes both light and deep sleep stages. It did not investigate rapid eye movement sleep, REM sleep, due to insufficient data.
Ah, okay. So we don't know how REM sleep is affected.
Not from this study. That's a significant area for future research, as brain activity during REM sleep is quite different.
And within the non-rapid eye movement sleep itself, were they able to differentiate between light and deep sleep responses?
No, the study noted that distinguishing responses between light non-rapid eye movement sleep, also known as N2, and deep non-rapid eye movement sleep, or N3, was beyond its scope.
I see.
So further research is needed on how responses to rough sounds might differ across these specific stages.
Makes sense.
Also, more investigation is needed to determine if acoustic roughness also enhances other perceived sound qualities, like perceived loudness, which could mediate these effects.
Meaning, does roughness just make things seem louder?
Possibly.
Yeah.
It's possible that rough sounds simply feel louder to our brains, even at the same decibel level. That needs more looking into.
So there's still more to learn about the nuances. What are some of the bigger unanswered questions this research sparks?
Well, a major unanswered question is the precise neural routes by which roughness directly targets emotional and attentional brain networks. How does it get there so fast?
Right, the pathway.
It's thought to possibly happen through non-canonical auditory pathways, meaning these rough sounds might completely bypass our usual conscious hearing system.
Bypass the normal hearing route?
Potentially. They could be hitting the brain's primal alert centers directly before we even consciously register them as a sound.
Like a secret backdoor to the alarm system.
Sort of, yes. This would imply a much faster, more primitive alarm system at play, but it still needs further anatomical and functional evidence, potentially from animal models, to really confirm that.
So what does this all mean for you, our listener, armed with this new knowledge about your incredible, vigilant brain?
We've seen how your sleeping brain is not a passive receiver, but an active filter, right? Granting privileged access to these rough sounds, even at low volumes, for our very survival.
It's a primal system keeping you safe.
A testament to our deep evolutionary heritage. It's pretty amazing when you think about it.
This deep dive reveals that simply reducing sound intensity isn't enough for true sleep quality. We must also consider the quality of sounds in our environment.
That's the key takeaway, really.
This knowledge isn't just fascinating, it's a powerful call to action.
So, What does this new understanding of acoustic roughness mean for how you might design your bedroom, choose your alarm clock, or even think about noise pollution in your city?
Good questions.
This isn't just about soundproofing. It's about curating your acoustic environment for true restorative sleep, understanding the subtle yet powerful acoustic properties that govern our unconscious minds.
Thanks for tuning in to the Health Headliner podcast by To Digital. Like and subscribe for more health news and breakthroughs. Stay healthy and informed. See you next time.